All right, hello AP students and welcome to your pre-lecture on titration or the analytical method of acid-base neutralization and quantifying the moles or the molarity of acid-base present in lab. And what we're going to do is going to go through a brief kind of overview of all of the logistics of setting up a titration, the factors to consider, as well as this very interesting role of an indicator. This is going to help us set us up for titration quantitative problems that we will be addressing regarding strong acid, strong base titrations, or any type of titration that involves a mix of a weak and a strong acid or base. All right. So this shouldn't take too long. My guess is about 20 minutes, but this is a really, really common AP FRQ portion of question where they have you kind of use your understanding of the logistical nature of setting up a titration to explain certain results. So one thing to consider with the qualifications for titration is that one, you definitely only want to have one reaction occurring between the two solutions you mix. So the idea is that you aren't having side reactions that could create a confusing result. The solution in the beret, right, in the dispenser is always known as the titrant. And the concentration of the titrant is always known. We call that often a standardized solution, right? To be a standard solution or a standardized solution means that you know its molarity. And then the solution in the flask with the unknown sample or the unknown molarity is always called the analyte because we're analyzing it, where X, the concentration of it is unknown. All right. We also want to consider when choosing a reaction, not only is it one reaction occurring between the two solutions, but we also want to make sure that the reaction goes to completion relatively quickly. Right, so you kind of want a reaction that has pretty good kinetics because you don't want to be waiting as you're dropping in drop by drop titrate. You don't want to have to wait between each drop 5 minutes to see how it's reacted, right? How many of the ions have been neutralized versus how many haven't? What's in excess, right? So you want a reaction that goes pretty fast. Like when I drop in that drop of titrant, I can see pretty thoroughly whether and to what extent it has interacted with the analyte. And then finally, you definitely want to be able to, when choosing the parameters for titration, you want to make sure that you choose the correct indicator, okay? Or the equivalence is occurring at a point in which an indicator can signal it. So what we are going to say here is that we want to make sure that our reaction, okay, is equivalences point, okay, be able to signal the equivalence point or that our reaction's equivalence point can be identified via an indicator. Okay. So just for a little illustration, okay, the kind of setup for a titration. Ooh, clearly my lines are not that great. All right. And don't forget, it actually counts down in the numbers. So you'll get like, this will be 35 and this will be like 36. Okay. Or to be actually more accurate, we tend to use 25 milliliter berets. So this will be 24. This will be 25 and it counts down. And what you have is this little dispenser, right? And what we say is we put our analyte, okay, our titrant. Wow, going strong already. Our titrant in the beret that is known, right? Its concentration is known. And then we drop by drop into a volumetric flask. Okay, and that kind of looks like a volcano, so let me fix that. All right, into a volumetric flask where our analyte is our unknown. And we say that for this titration process, in order to figure out the unknown, right? What we're doing here is in order to figure out the concentration of the analyte, what we have to do is we are trying to determine the moles or molarity, depending on what the question is asking you, of the analyte. And so what we do is we track the change in volume of the titrant, how much it is required to reach equivalence. And equivalence, right, is signaled, the equivalence point, the point at which the moles of acid are stoichiometrically equal to the moles of base. So I have been fully neutralized. Okay, we are for a strong acid, strong base, we're at a pH of 7. For weak involving acid or bases, it changes a little bit, but either way, we have fully neutralized the analyte. Okay, we say that once we figure out how many milliliters of titrant is necessary to reach equivalence, as indicated by the endpoint of the indicator where we see color change. The endpoint is where we actually see the color change. The equivalence point is the understanding at the mole level, the particle level, that we multiply the volume required to reach these equivalent points. And we say, okay, whatever amount of titrant volume I've used, I can multiply it by the titrant's, okay, I can multiply it by the titrant's molarity because it's known by the titrant's molarity. Let me get in the same color, so I'm color coding. And that'll give me the moles of base or titrant. Okay, and that's probably a better way of saying it, moles of titrant. And if I know the moles of titrant, what I can do is from the moles of titrant, I can use stoichiometry or my balanced chemical equation, however many moles of acid per moles of base, okay? And I can determine the moles of therefore acid present. All right. And once I know that the moles of acid that are present, okay, I can say, well, however much volume was in the analyte container, I'd simply divide by the volume of analyte, and I get the molarity of my unknown, right? So that's just kind of an illustration. I'll do a little demo in class, and you guys will definitely be doing a lab on titration when we get past the AP exam. Okay, so let's talk about this indicator because this indicator is really interesting chemistry in its own. All right, so an indicator, of course, we already know is some type of chemical species that we add in that doesn't react with the actual reaction theoretically, right? It isn't going to produce some other product that is going to confuse our results, but that is used to signal when we've hit equivalence. Okay. But more specifically, that's a very conceptual understanding of the indicator. More specifically, the indicator is actually a weak monoprotic, so one proton or one H plus able to be ionized acid, okay, with a conjugate base pair with a conjugate, well, with a conjugate base that displays a different color at equivalence between the titrant and the analyte. All right. So what we're seeing here is we're seeing that we're actually having an acid-base reaction between the indicator, but we're pairing it or aligning it with the acid-base reaction, and particularly the equivalence point of the acid-base reaction between the actual titrant and analyte solution that we're examining. And we're using it to mark, okay, where and when we've reached equivalence for the actual solutions that we are interested in. So the general indicator equation, or the general equation that we use to kind of quantify or express this kind of sub reaction or sub acid base protonation and deprotonation with the indicator is the following. We say that the weak monoprotic indicator with an H plus that's able to be removed and donated is in water. Okay. And what happens is it's going to be in equilibrium because it's a weak acid. So it's going to be in equilibrium. And it's going to produce conjugate base indicator without the proton and acidic water, or H3O plus hydronium ion. And what we say is that the protonated and the deprotonated version of the indicator species must have distinct colors. So whatever color this is, let's say it's yellow according to the indicator, this must be blue or something different. And what we say is we would like that the color change, okay, occurs at the same point of the equivalence being reached for the actual titrant and analyte. So how do we understand indicator behavior? Well, first and foremost, color change occurs over a range, all right, of pH values, and indicates when the concentration of protonated indicator is equal, or I guess you could, yeah, is equal to the concentration of indicator with deprotonated, because we're in a 1-to-1 monoprotic ratio. And so initially, what I mean by it occurs over a range, because you're like, no, it doesn't. Well, if you do a titration, and when you do a titration, you'll see this, as well as if you look up a video of titration or you watch my demo carefully, you'll see that we see flashes of color change, but it doesn't stay very long. So at the first side of color change, all right, we say that it's when one, the initial solutions are mixed and not distributed well, but two, quantitatively, we kind of describe that as the point at when 1/10 of the initial indicator is converted to conjugate base. So what we would say is that the concentration of indicator deprotonated over protonated indicator is equal to 0.1. Okay. And then at endpoint, which should line up, right? It should align with equivalence point between the actual titrant and analyte that we're focusing on. At endpoint, we say that the concentration of the indicator protonated is equal to the concentration of the deprotonated indicator. So we have the same amount of acid to conjugate base present in solution. And at this point, we see color change, permanent color change. Okay. And for us, we talk about it as being identified as the faintest pink, because we often use an indicator. We tend to use universal indicators or bromethyl blue that actually goes from pretty much clear, not actually not, or like blue to very faint blue to a very faint pink at equivalence or endpoint, depending on what perspective you're taking. Endpoint is the indicators terminology for it because it's specifically talking about the color change of the indicator, but equivalence is the angle that we really care about, which is the titrant and the analyte having reached stoichiometric neutralization. Okay, but we often say that it's when we see the faintest of lasting color change, which is usually a pink color. Okay, and then we can continue to add more of the titrant, and what you'll see is that we kind of blow past neutralization and we get a deepening of the color in the indicator. And we say that the completion of color change, where you don't see any more intensifying change of the color, or you don't see any, new color, let's say, occurs when, all right, the indicator deprotonated concentration over the protonated indicator's concentration is in a 10-to-1 ratio. So what we say is that you've overshot. If you get to completion of color change in the indicator, that's actually indicating to you that you've overshot your titration and that you've way blown past equivalence and neutralization. Okay. So this is kind of like a little table kind of showing you. And what I want to point out to you that will become incredibly relevant for us is this right here. That for a weak acid, such as the indicator, at endpoint or at equivalence, pH is equal to the pKa, or the negative log of Ka. Okay, so this is just going to become something that becomes very important. This relationship right here is going to be incredibly useful for us as we analyze weak acid base chemistry. And this only applies for weak acid base chemistry. Okay, we'll talk more about it in the future, but the indicator is also giving us a little sneak peek into the future as we consider moving past strong acid, strong base, and into weak acid, weak base understanding. All right, but the big idea is that we also notice that the indicator colors change over a range, how we said that it occurs over a range of pH, is a range of plus or minus, well, it's actually a pH range of 2. I'll just put it this way. It's plus or minus 1 or over a pH range of 2. Right? So what we see here is pH is equal to pKa minus 1 all the way to pH is equal to pKa plus 1. So we see a range of pH indicator of 2. Okay. And what you might want to consider recalling or reminding yourself of is that what exactly does pH mean? So pH is equal to the negative log of the hydronium ion, or the H plus, and that pKa is equal to the negative log of Ka. And don't forget that the greater the pH value, the less acidic it is, so the more basic. And the higher the pKa value, the less acidic it is, so the more basic. But the higher the Ka value, the more acidic, right? So that just might be a quick reminder of some of the mathematical relationships when you're looking at these just terminology of like pH, pK. Okay, what does it really mean? Well, this is what it really indicates to us and what it reveals to us, okay? So a couple important takeaways just to summarize everything is that at endpoint, aka transition point, is another way of putting it that you might see in a couple books if you rent the Princeton Review, or if you're looking at more older material. At endpoint, aka transition point, or of course equivalence point, what we see is that for the indicator, we see that the indicator are weak monoprotic acid. The indicator has a pKa that equals its pH, and i.e. it signalizes, oh my goodness, it signals, right, the equivalence of our titrant and analyte. And then, of course, it's important to know that the indicator color change does occur over a range of 2 pH units. All right. And that when choosing an appropriate indicator, right, which can be a type of AP question, when choosing an appropriate indicator, you want to look for an indicator whose pKa plus or minus 1, i.e. the pH range of 2, aligns with the pH, okay, of equivalence for our acid-base neutralization, of equivalence point for the titrant and analyte that is actually the focus of the study. And then most importantly, but it's kind of also not yet because it really deals with just weak acid, weak base chemistry, which is far more complicated than strong acid, strong base. We can estimate pH and pKa at indicator equivalence because this aligns with the halfway equivalence point where half of the acid has been neutralized for a weak acid or weak base titration. And again, I put a star here because this is a sneak peek. This kind of little star does not apply for strong acid, strong base chemistry. Because we know for strong acid, strong base, neutralization is just pH at 7. But this right here, this indicator study is really giving us a sneak peek into future topics. So quickly, what we have here is a quick table about various indicators that we use. And oftentimes what we do is we actually combine a ton of indicators that have different pH ranges to cover the full spectrum of the pH scale. And we call that a universal indicator. So we often use a universal indicator. And notice I say that oftentimes our color turns pink. Lots of our pH transition points or equivalence points for the labs that we do in class tend to fall in the phenolphthalein range of our universal indicator combination, but it doesn't have to be. And so what we see is, here's a quick sample problem. I'd like you to come to class with your answer to this sample problem question. And it's just a quick, easy kind of practice on how you can use your indicator understanding to predict and select the best indicator for a given reaction. And I look forward to seeing your guys' answer.